Good morning, everyone. We are Team 45 in an era where AI generated audio is becoming nearly indistinguishable from human speech. The security of our voice based system has never been more critical. We are excited to present our CMU 11785 final project Dual Teacher Knowledge Distillation for Joint Speaker Verification and Deepfake Detection. Our team, Lucky Gurjar, Aryan Singh Chandel, Nikhil B, and Tanuja Bhatt, has spent this semester exploring how to make this system both smarter and faster. We are incredibly grateful to have worked under the mentorship of Professor Masabali, who helped us navigate the technical challenges of modern model distillation. To understand our motivation, look at the current industry standard. Right now, securing a voice-based application requires two entirely separate pipelines, one for speaker verification, identifying who is speaking, and another for deep fake detection, verifying if the speech is real. This is inefficient. It effectively doubles our interference cost, increases latency, and forces us to maintain redundant infrastructure. Worse, these models act in isolation. They fail to share the rich, overlapping acoustic features that distinguish human voice from an AI generated clone. To walk you through how we achieve this, we have structured our presentation into three logical paths. The approach. Our architect Aryan will explain the dual teacher distillation strategy and our data pre-processing pipeline.
Thanks for that introduction. Let's dive deep into the technical backbone of our project. To achieve joint speaker verification and deepfake detection within a single lightweight pipeline, we are re-implementing a dual teacher distillation framework. Why dual teacher? Because specialized tasks require specialized knowledge. We selected ReDimNet as our teacher for speaker verification and Assist for our teacher for deepfake detection. We are using web-to-vector based backbone. This allows students to inherit the strength of both experts without carrying the combined weight. Data quality is the foundation of any distillation process. We utilized FoxLab1 to provide the diverse and real-world dataset, and we are using ASP Spoof 2019 dataset to provide the synthetic audio necessary to running the deepfake head detection. To ensure consistency, we are using standardized audio of 16 kHz. We are processing them in 4-second chunks to maintain a manageable temporal context. Our student architecture is designed for efficiency. At core, we use this web-to-vector based transformer, which acts as our feature extractor. We then feed this into bidirectional long short-term memory aggregator. It captures long-range dependency in the speech signal that a standard transformer might miss. We implemented two separate projection heads on top of YLSTM. Now I'm passing the floor to our ML engineer, Nikhil, to discuss exactly how we implemented the loss function.
We use cosine distillation laws to align the student with our teachers. Training occurred in two phases. First, we trained only the projection heads. Second, we unlocked the full model for end-to-end fine-tuning. The results show strong convergence over 15 epochs. Total loss dropped from 1.56 to 0.05. We achieved final SV loss of 0.0029 and DF loss of 0.0023. We have currently finalizing the EER and AUC metrics to quantify the performance gap against the full-size teacher models. Now, I hand over the mic to Tanuja to wrap up the findings and discuss where we see the technology headed in the future.
Thank you, Nikhil. To wrap things up, I would like to highlight what this project means for the broader field of speech technology and where we see this work evolving. Our experiments have yielded a successful validation of the dual teacher distillation framework. We have demonstrated that it is possible for a single compact student model to effectively synthesize knowledge from two disparate specialized expert without sacrificing performance. However, we see this as just the beginning. Looking ahead, there are two major areas we are eager to explore: task adaptive loss balancing, streaming interference. It is also important to acknowledge that none of this world have been possible without the robust foundation provided by the research community. Especially, we use the Wave LM framework as the backbone of our self-supervised student model, which provided the high-quality feature representation necessary to make the distillation work. Thank you all for your time and for listening to our presentation. We'd be happy to take any questions you have at this time. If you think anything later or if you'd like to dive into the implementation details, please feel free to reach out to our team on Piazza.